Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Matrix. Thank you very much. So the model I'm going to talk about is a very basic one. I think it was okay. So we consider square matrices of size n. And the entries are i.i.d random variable. And they take on value 1 and minus 1 with probability half. That's what we call random Bernoulli matrices. Okay, so there are lots of basic questions about this model, and lots of them has not been answered. One question which was I think the first question we look at seriously was to determine the value of the determinant of Mn. And I think the guy who started this study was Komlos, who very early, I think 1967, published a paper about this, and he proved that almost surely the determinant is not 0. Right. And you can observe that the determinant of this guy is always divisible by 2 to the n minus 1. So this implies that at least you have some non-trivial lower bound. The conjecture for the determinant is something like the right order of magnitude of this guy should be of order n to the n half. And the intuitive way you think of it is, well, you look at the matrix. Right? The absolute value of the determinant is the volume of the box spanned by the rows of this matrix. And now you take any two rows. You will show that with very high probability they are more or less orthogonal to each other. Right? So what you expect is from this box is that it looks like a cube when every edge has size about square root of n. That was the intuition. And from above it is very simple because this is always true with probability 1. That is less than n to the n half, which is the Adama inequality. On the other hand, this conjecture was open for a while. So last year, Terry Tao and I proved it. So we can prove the conjecture is indeed the case. Now, Komlos' result can also be looked at in a different way. Equivalent way to state it is that almost surely Mn is non-singular. Right? So namely, the matrix has full rank. And then, naturally, from here, we want to ask that what is exactly the probability that Mn is singular. Okay, so let me give a definition. If I say that Pn is the probability that Mn is singular. Yes?
I mean, another plausibility argument for this would be that there are n factorial terms, there are pluses and minuses. So that would lead you to think that perhaps it behaves like a sum of n factorial quantities. I mean, are there more at least conjectures about how this is distributed?
I don't know. I don't know how to prove anything about the distribution of the determinant. We just have a lower bound.
But there is this central limit theorem for the determinant of plus minus 1 matrices that's been proved.
Yes, there is.
Yes.
I
I
think
mean, the
there is.
distribution is known. You know what you need to normalize it by to get a Gaussian in the limit.
Yeah, I think we found it out like a few months ago, and nobody could understand.
Yeah, but it's known that you look at the determinant of plus minus 1 matrix, you know what to normalize it by so that you get in the limit a Gaussian. So in particular, the asymptotics of this determinant are known exactly. This little o of 1 in the exponent.
Yeah, but I don't bet on the proof.
Yeah, so the first thing was...
Well, we tried very hard to reach this proof, and we cannot get the first two.
It's quite old, right? It's from the 80s or something.
So, yeah, I don't know. If somebody can explain this to me, it would be very, very useful. But I think the guy had a similar result. He like kind of that, and people didn't understand, and then they have to reprove it.
So Turán and Szekeres had an earlier result.
Yeah, Turán had proof. Yeah, they compute the moment of this.
So what's the little log n term? So what is the little log n term? According to
yeah, it's something like square root of n. Square root of 1 over n. Okay. But yeah, I'm going to focus on the second. The singular question, which is, well, let us formalize the Komlos result in this form. Okay, so the question is to find, well, Komlos result can be restated as Pn is ln over 1, and actually his proof gives the 67 proof just gives something very slowly, 10 to infinity, something like 1 over log n. But the conjecture is something much stronger, so the conjecture is, it is a quite well-known conjecture, and usually people refer to it as notorious because it's look quite impossible to how to do it. Okay, so let me explain why you have, well, 1 over 2 to the n is simple because that is a probability that you have 2 equal rows. The first row equal the second one. So you have this 1 over 2 to the n, but of course you have the choice to take any 2 rows you want, so you can multiply it with the factor n over 2. Instead of the row, you can do column as well. So you have another factor of 2. And instead of 2 rows equal, you can say that they equal up to psi. So you have another factor of 2. So that is a proof of the lower bound. Well, of course, there will be overlap somewhere, but that's why you have ln over 1 here. And so it says that basically the reason for a matrix to be singular is to have 2 equal rows. So let me rewrite it. So maybe half plus another 1 to the n. So in a later proof, Komlos have a different proof of his result and give a better bound on Bn. I think it's something of order 1 over square root n. Probably, I don't know when. It was published in Bolobach's book, but
It wasn't published.
yeah, it was not published as a paper. It was published as a part of the book, Random Graph by Bolobach. Sometime around the 80s. And there was a breakthrough by Komlos, Kahn, Komlos, and Szemeredi. In 95, when what?
Yeah.
Seemingly interjected. You see
Yeah,
that?
And this is the first time we have an exponential bound for Bn. So we have something 0.999. Yeah. So 1 minus epsilon. And the result I will try to talk about today is a recent improvement again with Terry Tao, that we can push it down to roughly 3/4 to the n. Okay, so first let me, before going into the proof, let me raise a few questions. For instance, I am thinking of a common strengthening of these two results. So we here prove something like almost surely the determinant is what it should be. Right? And we know that exponentially it is not 0. So if we have a common strengthening, I may want to ask that is it true if the probability that the determinant is small, say less than n to the 0.4999n, right? So a little bit less than half is exponential, something like this. So that is one possibility. And well, I think it should be true. I don't see any reason why it is wrong. So another model I also like to mention is the symmetric model, which is very common in the theory of random matrices, of course. That we have Qn, everything is the same, but the matrix is symmetric. So namely, we have only the upper triangle bits are independent, but the rest is a reflection of this. And you can ask the same thing as before. And it has been asked, I think, there's the question of Benchy ways. And first of all, well, at the very starting point, that is it true that almost surely the determinant is not 0. It was asked in the, I think, sometime in the 90s, perhaps. I don't know. Maybe even earlier. Gin and Nati told me the question last year. And it is very natural. Maybe other people can ask it as well. So by beginning of this year, a student of mine and Tao and I can answer this question positively. So it is indeed the matrix is non-singular, And then the rest of the picture is waiting for you to complete it. So right now, if you shift the question from non-symmetric to symmetric, then we are in the stage of Komlos 67. So I don't know how long it will take to do the other stuff. Yes?
If you take 0, 1 matrices instead of 1, -1 matrices, are the results the same?
Yeah. It's very simple shift. Like if you have 1 minus 1, first of all, you can assume that the first row is 1, and then you just subtract every row of this, and you will have a matrix. It's 0, 2. And actually, lots of the results here can be generated for other distributions as well. Yeah, so there are a lot of questions one can ask. Yeah, but the symmetric one seems very hard now. Yeah, it should be. Well, I conjecture it should be the same like n to the n. And also the singularity properties. So okay, so we like to talk about this Pn and.
Is there any, how many eigenvalues and how are they distributed around 0?
Yeah, so that is the problem. Well, we know the distribution of the eigenvalues, but at the rough scale, right? So the scaling is little of 1. So for instance, we don't know how close is the smallest one to 0.
Will there be many near 0?
Yeah, there would be a few. Yeah, for instance, if I take the Qn, there is Wigner semicircle law saying that all the eigenvalue are between minus 2 square root n and 2 square root n. Yeah, but so actually the number of eigenvalue between minus 1 and 1 is roughly square root n. Right, so there are lots of small ones. And we don't know that if the smallest one can be even exponentially small. That we don't have no idea.
Let's say the expectation would be that those square root of n are sort of uniform in there. So no.
There are some, I don't know, there are some numerical experiments which are pretty amazing what happens with the spectrum. And somehow the eigenvalues tend, I mean, just judging from a picture, no proofs or anything, the eigenvalues tend to drift away from the x-axis when you do this. It's pretty...
But at least as the smallest one is concerned, so less lambda mean, the one which is closest to 0, then I think the general conjecture is that 1 over lambda mean, say in absolute value, has the expectation order square root n. Yeah, so it's roughly 1 over square root n.
So that's what you would expect from the end of...
Right. And right. And for Gaussian, if the entries are Gaussian, this is true. I mean, people even prove distribution about 1 over lambda mean. So, so the discrete distribution has a big role here. Right. So so let me start with the singularity. So we know that the Kahn, Komlos, Szemeredi theorems have to put a slash everywhere. This 0.99 to the n, and we go now to 3/4 to the n. Right? Well, actually, there's the middle step. What we did sometime last year is that we don't do this directly. We have to go to a middle step when we slightly improve this bound to something like, I think, or something like this. Now it is actually a very important step to us because, well, this 0.999 look ad hoc, but actually you cannot improve it very much. By tightening the calculation, I think in the paper it was mentioned, like if you tightening all the calculation, you can go to 0.998 or something, but not much more. So actually, to do this, you need to, so what we did, we follow all the general ideas in the KKS, but we have a simplified proof, which sort of give a clearer, quick picture that what one should do to get to 3/4. And the 3/4 have its reason. So I will go back to this at some point, but 3/4 come out because of the following very elementary inequality. So I state that cosine of x in absolute value that's important is less than 3/4 plus 1/4 of this. And it is not true if you reduce 3/4 by any amount. It's not true anymore. Right. This guy is exactly half plus half of cosine square of x. So somehow the reasoning is sort of more or less optimal. At least we do something very tricky with this. Well, not with this, but the way it was applied. So now both proofs are still very long. Well, this is really relatively long, and this is very, very long. So what I try to do is to, well, tell something about the beginning of this proof. So you will see what the main idea is. And then I drop that and go to the beginning of this proof and show you what kind of observation lead us to this. And then if you want, we can talk about the details some other time. Okay, so the starting point. Okay, so let me tell something about this, and the starting point is well, as it was done in the KKS paper, is the following. We look at probability. Say, all right. So first, a few notation. You have mn here, and I will expose it row by row. So we'll have n random vectors, x1 up to xn. Each of them had n random bits. So the probability of the singularity probability is well, the matrix is singular if x1 up to xn span a proper subspace. Right? So it will be equal to this probability. I take all possible proper subspace and sum it over this. Right? And if you want the sum to be well defined, then you just have to restrict the set of subspaces to a finite set. Okay, so first of all, well, it is a relatively easy exercise that you can see that it is enough to sum over hyperplanes. Okay. Yeah, so I will in the presentation, I will omit a lot of steps like this, which are relatively simple. All right, so the next trick is, okay, now we have to handle this sum. So the idea is to break it into to 3 sums right. So I define the richness of V by just the number of 1 minus 1 vectors on it. Right? So say a very bad notation, the cardinality of V is a number of random of the vectors in this. Okay. And rich means that V has a lot, poor means that it doesn't have a lot. And middle class is the rest. And the rich guys and the poor guys are very easy to deal with. We more or less can control their contribution tightly. The troublesome guys, as always, are the middle classes. Right? And there you have to do hard work to know what they contribute. Also, yeah, so the definition of rich is something like this. Rich is if cardinality is at least, say, 100 times 2 to the n over square root n. Alright, and poor is, well, poor is sort of tricky, so let me say that's something like, say, 2 to the minus epsilon n and 2 to the n. So the number of vectors in the poor guys is exponentially small compared to the size of the space. And the middle class is something in between. Now the rich guy is easy to handle because of so-called Leeuwenhoek-Oakford-Erdős theorem, which says that if V is rich like this, then the normal vector of V should have lot of 0. So, okay, so let me write it this way. Now, if I fix the V, so V has normal vector, say A1 up to AN, and X is a random vector, so X is a random vector, epsilon, or psi 1 up to psi n, when the psi are Bernoulli random variables. So this probability is a probability of sum of AI epsilon I equals 0, right? And there is a well-known lemma usually referred to as the Leeuwenhoek-Oakford-Erdős lemma, saying that if, say, A1 up to AN are non-zero, then this probability is less than 1 over square root n. Well, actually, to be precise, it's less than the middle binomial coefficient. If you want. And then this guy is very rich. That means a lot of the AI should be 0. And for that case, we have from the KKS paper, or even there's an argument back to the Komlos paper in '67 to handle that case relatively easily. So we take care of the rich. Now, for the poor, there's a very nice argument, very simple but effective. Okay. So we are summing this probability. Right. Now, but since V is a hyperplane and you have n vectors, so there are n minus 1 of them which already span the hyperplane, right? So it will be less than this. And probability, say, x1 up to Sn minus 1 span V, and probability that Xn should belong to V. Right? Then you have to multiply by a factor of n because we specify Xn, but It can happen with anyone or any coordinates. But since the V is poor, by definition, the probability that xn is in V is less than 2 to the minus epsilon n. Right? So it will be equal n to the less or equal n to the 2 minus epsilon n, the sum of V poor probability of this. But this sum is less than 1, less or equal to 1. Because, oh, this guy should spend something. And so here you get 2 to the minus epsilon n free. Yes.
You said that you insisted that you want to slice the pool at this level, but it seems that you could, I don't know.
Yeah, so epsilon is something I have to optimize later on. Right? It is a constant, but I will have to. So the bound I get, the exponential bound I get at the end is 2 to the minus epsilon n. But I have to optimize epsilon. Right now I just leave it free. Okay, so the main part of the proof is to handle this middle class guys. Okay. So the key idea from the KKS is the following observation of Hollas that, okay, so let me fix this. We have a coefficient, say 1 up to an, which is supposed to be the normal vector of V. Now we have the Bernoulli random variable, which is minus half and half, or minus 1 and 1 with probability half. And now, for any constant mu between 1 and 0, I define another kind of random variable, epsilon mu, which can be 0, minus 1 and 1, and which is 0 with probability 1 minus mu, mu over 2 and mu over 2. Okay. So now we look at two kind of probability. The probability that this guy equal to 1 compared with the probability equal to 0 compared with this probability equal to 0. And as it was explained in the KKS paper, that you can think of it as a random walk, right? So you have a random walk with step size ai, and you are talking about the probability returning to the origin after n steps. Here you have a lazy random walk, right? So this is 0 with probability 1 over mu. That means you stay at each step with this probability. And so intuitively, you would expect that this side is larger than this side. And in fact, more is true. Actually, it can prove that this will be less than even with some constant depending on mu. Constant less than 1, of course. Okay. So that was probably the most important idea in this proof. Okay, so now we try to use this to our advantage. And the scheme is the following. Okay, so we talk about this probability. V, right? Okay, so let me cheat and say that this is something roughly like, now big question mark means that actually I cheat big time. What I want to say is not even true, but let's do it anyway. You can replace the span V by just the event that this guy belongs to V. Right? So we suppose that we have a hyperplane, and you pick random vector, and all of them belong to V, then they actually span it. So namely, the subspace in V doesn't have too much weight in it, something like that. All right, so assume that we cheat successfully, then this by the key observation here should give us an exponential gain, right? Say, now, well, instead of x, I will have x mu, and you already know what it should be, right?
Don't you need an upper bound? And if they span it, then they certainly are in there. Or...
Yeah, but actually, unfortunately, that is the wrong way. Upper bound here is fine, but I want to claim that they are the same, because I have to use it both ways.
Okay.
Yeah. Right. Okay, so xi mu is the random vector consisting of coordinates epsilon I mu. Yeah, and now we have to, as Rossi said, we can have a bound here, but now we have to do it in the other direction too, to say that this is roughly okay. Now, if we xi mu is vector. Oh, x is, well, let me say x mu is a vector like this. And xi mu are copies of like this, x mu. Okay, so if we can do this matrix, then we finish the proof the same way as before. Right? We sum up over V. Can sum up over V. This is the probability we are interested in. And this is bounded from above by C to the N. Right? Because this is again bounded by 1. So we have exponential gain. Okay, so the idea is that, well, this is not quite, oh, well, this is true, but this we cannot do this. But we can do something close, and that sort of makes the proof go through. Right. Yeah, so there are relations between mu and C mu and epsilon that I had before, and the result we get from here is just got from the optimization of this parameter. Together, they have to satisfy certain constraints.
So you're using the fact that this is a middle class only in star, or also later in the argument?
Yeah, we need it only for the middle class.
Yeah, but later on, are you using it again?
Later on, we mean when?
The rest of the arguments.
There's no rest of the argument. The middle class is the rest of the argument.
No. In the justification of the rest of the question marks, does it come in again that you need a...
Yeah.
It comes in again.
I mean, in other words, a natural question to ask is why do you have to spin? This argument works. Where does it break? Why doesn't it come?
So there will be some delicate relation between the way you have to set epsilon and mu. Right? There are some constraints. These two have to satisfy, and if you increase epsilon, then somehow you have to change mu as well, and that's the trade-off. Yeah, where you cut the definition of poor will affect the bound you get in the middle class. That's what I want to mean.
The question is, for example, suppose this was a rich space. What will break?
Well, we don't care about the rich, right? The rich
No.
is...
Just to understand, what will break?
What do you mean, what
This
break?
question.
doesn't count because it is equal.
What
But there's no plan for
what
those.
is not working for a rich B?
Why couldn't this be the whole?
I think it would work for the rich B as well, but for rich we have a much better bound. There's no reason to do this.
I mean, why do you have to distinguish rich?
Oh, yeah, right. I think in the proof of this we have to assume that the thing is not rich, because when you do this, we want many of the AIs are not zero. If O of the AI are zero, but one, then this thing will not give you anything. Yeah, right. Yeah, I thought, yeah. Let me see. Time. Oh, there's time over there. It's time. 15, I think I don't even finish the first part of the first result. So anyway. Yeah, so now I will be a little bit quicker and force you to believe many things you don't want to, but there is no other way. Okay, so I will specify this lemma a little bit more. So here's the lemma. That, okay, if we pick V in the middle class, then we have this less than half of probability. And I will specify the value of mu2. And you are right to ask why, but it's 1/16 is the result of some optimization that we don't want to go into. So that is the more precise version of this. And I will go back to the proof of this because it will be important to see this proof to understand what the 3/4, at least the beginning part.
This means that you change 15/16 of the coordinates to 0.
Yes. And the more I change this to 0, the better, right? If I have mu say equal to 0, then I can put an even larger, a smaller constant.
You change all of them to 0. Then
Yeah.
of course
Right. So there's also, that's what I say about the relation between mu and C mu. There's some trade-off between these two. If I want mu, I set mu smaller, then I gain here, but then I will have trouble at other places.
But
This for all V? This for all V? This is for all types of V?
Yeah, this is for the middle class one. Yeah. Okay, so the definition of poor is poor is something like 2 to the minus epsilon n times 2 to the n. I will use notation D is epsilon n. So D is sort of the codimension of the plane, the discrete codimension of the plane. And so I need a quantity gamma, which is roughly D divide, so n times log base 2 of 16 over 15. Okay. And well, this will be clear why I have to set it this way. Right. Okay, so now I will try to execute this plan. But we have to do something a little bit different from this. So namely, the idea here is, in this plan, we try to change every x to x mu. Right? But in the real life, we will be able to change only a fraction of this to x mu. But if you are able to change a fraction, you still gain exponentially. Right? So now let me consider the following event. So I want to pick 1 minus epsilon n vectors. And I want to consider the event that these guys are linearly independent in P. Okay. Actually, for a practical reason, I will rename a few of these guys. To x prime. The reason is that I'm going to switch this guy from x1 to x1 minus gamma n to x mu, but I will keep the other guy unchanged. So every vector in this row is still a copy of x. So let it be the event number 1. So the probability of this event is clearly lower bounded by the probability of x belongs to V to the power 1 minus gamma to the n. Right. And it is roughly what? It is oh, epsilon, I guess. Epsilon, sorry. Right.
Even then I don't see the direction.
Well, this is the event.
To be linearly independent, they certainly have to be in there.
Oh, yes. So it's up about. Yes, so it will be something like so this probability is what is the right way to write yes, 2 to the minus epsilon n to 1 minus n. I want to put this letter d in, so let me do this is just some nonsense thing. So when capital N is 2 to the n. Okay. Right, so now I'm going to consider the event when I am going to switch the first guy by x mu.
Where did you get this 2 to minus epsilon in there? This x?
That is the probability that x is in V, right? And the size of V is roughly this.
I thought that was just a lower bound on the probability.
Yeah, so, right. We can do it in details, but let me cheat again. Because the main idea is not here. But, okay, so the event we really want to consider is event, say, let me call it by a name AV, is what happens if I switch the guy xi to xi mu, and I still want them to be independent. Right? Independent.
So you're also supposed to deal with terms in the middle group where there is no epsilon. So
Yes, yes.
do it later.
Yes, yes. Yeah, no, I said that there will be a lot of questions you want to ask. There's no time to answer this because the way, I mean, normally, I mean, this may need like 2-3 hours to present in details, and the other one may need like double that if I am about to answer this kind of question. So now we have to trade off. Either I present the main idea and we add question later, or we add question now and stop in middle of nowhere. So that is the plan. Yeah, but all this correct. I mean, there's a lot of, I guess, there's several places that we have to put either big question mark or small question mark. All right, so the claim here is that by the switching, we will gain something compared to this bound. So this probability that the event, this AV hole, will be larger, slightly larger than this. We still have this same thing. But now we gain an important factor of 1 minus gamma, namely the number of. So what we gain is n to the 1 minus gamma, which is 2 to the 1 minus gamma n. Right? So namely the number of coordinates you change. And that is what you would expect because each of them you change, you gain a factor half. Okay. Okay, so let me try to prove this, or at least to give you the intuition why you will see that why the definition of gamma is sort of important, that you have to define gamma that way. All right, so the way we write the probability of event A is that we can do this. Conditional probability is a condition on AV prime. And what is AV prime? AV prime is just the event that all of this vector belong to V, right? And AV probability that AV prime is more or less exactly this already. So I have to take a little note of 1 here. Because you have, yeah, so if you look at the probability that all of these things belong to V without the mu, then you have this, right? And by changing the xi to xi mu, you gain half here at 1 minus gamma n places, so you gain this guy. And then there's some error term, which is of order little of 1. So it is already like time what we claim to be. Okay. Yeah. And yeah, if you puzzle about even 1, just forget it. That is just something I tried to as intuition, but it failed, and it fails. We just concentrate on the event AV here. So we claim a lower bound on this, right? And here we already have that lower bound. So what you have to show is that this guy doesn't contribute anything. Right? So we want to show that whether it is just n to the little of 1 or not. Okay?
So what is AV prime UN?
AV is just that this guy belongs to V.
No,
right?
AV prime.
Yeah, AV prime is that this guy all belongs to V. So here I say that if they all belong to V, then with very high probability they are linearly independent. And with very high means something sub-exponential, basically that. Okay.
So how is that? Can in general, conditioning on being in V, I mean, normally these would be linearly independent.
Yeah, so that depends on how big a subspace.
1 minus epsilon.
Yes, so that's the point, right? So the trouble here that you have to forbid that there is a very big subspace in V that contains, say, much of the vector, then this thing will surely fail, right? So, yeah, so that's the reason why we have to define gamma this way. Right? So now let me recall that probability axis in V is roughly 2 to the minus d. Right? Again, I concentrate on the boundary case. Yes, will work for the smaller d is actually the better. And we have probability x mu in V is roughly twice as much. Now, what is the trouble when I consider a V, say, yeah, I want to expose this sequence vector 1 by 1, right? And a V would fail if, say, at some step, this guy belongs to the subspace spanned by the previous guy. Right? So say AI. Okay. So let W be the subspace spanned by this. Then the probability that Xi 1/16 belongs to W is what? Well, I claim that it will be less than 15/16 times the codimension of W. Okay. Now, if you want to see it, it is easier to see the general case. Say, the claim is, say, like Px of mu belong to this is less than 1 minus mu to the codimension. So this is the general claim. It's terrible. No, I think it should be like mu half instead. Yeah. Oh no, it's 1 minus mu. And this, you can prove this by just compute the maximum weight of such a subspace. Because a subspace is determined by the number, the subspace of dimension d is determined by d coordinates. Right? So basically you can fix the coordinates and compute the weight of the rest. Yeah, so I think the toy problem that you will see very easily is that if omega is of dimension, say, m, or W is of dimension m, then W cannot contain more than two to the m vectors from the -1 vectors. And this one is just a generalization of that.
But why is it relevant? So
oh, this is relevant because we will have the following bound, the conditional bound, that Okay, so now assume that this guy is already in V, right? Then we have to multiply by 2 to the D. Times this, right? And well, we want this to be bounded at least from above by 1. Okay? So that means you cannot have the dimension of W very large, the dimension of W very small, right? And that means you cannot set, I mean, if you want to set it equal to 1, then gamma here is the right dimension.
I think I don't understand this. Why is it enough to go to in W to the first 1 minus gamma n? So why couldn't it happen that some later one depends on it?
Oh yeah, the later one we have to do this calculation again, and it's actually a little bit more complicated, but at least at this level it explains why gamma should be set that way, because you see the log base 2 of 16 over 15 right here. But yeah, so yeah, and this only take care of the mu part. The other part you have to do conditional probability again, and a little bit more complicated. So let us like swallow this claim again with more questions. That more or less this thing you can execute fairly easily. Now, okay, so now we will see that why the claim will give us the type of bound we want to do with this switching trick, right? So now, okay, I fix V, so let BV be the event that, say, x1 up to xn span V, right? And AV is the same event over here. So I'm going to work with these two events. Okay, so we can start it this way, the probability. Well, the probability of BV is what we really care about, right? We want to upper bound this. So it will be the probability of AV intersect BV divided by AV. Because I think both AV and BV are independent, right? All the random variable, all the vectors we talk about here and here, they are independent. Okay, we have lower bound for AV in the claim. That means we have an upper bound for this guy. Right? So it will be less than n to the minus. Well, we just have to take the reciprocal of this guy. Right. Okay, so now we look at the AV intersect BV, then we have a bunch of vectors, right? So we have the first n we talk about in BV, and the 1 minus epsilon n we talk about in AV. Okay, so all these guys are independent vectors. Now, since these guys are independent, then we can choose, and they have dimension 1 minus epsilon n. So we can choose an epsilon n vectors from here to make a full space. Right? Oh, well, we can have like epsilon n minus 1 vector from here, which together with this Greenspan V. So we can assume that this vector, the x1 up to x epsilon n minus 1, and the minus 1 will not play any role in the calculation, so let me just replace it by epsilon n. And by this assumption, I have to pay a factor n to the epsilon n. Okay. So we will assume that this guy together span V. Okay. And let's denote this event by C of V. Then, okay, it is a rather crude bound that we have here, that we still have this guy. Plus of 1. We have this entropy loss. Which is roughly n to the entropy function of epsilon. And we multiply with the probability of CV. And the rest, well, we have to say something about, well, after we throw this guy, x1 up to x epsilon n, to this spot, we still have to say something about the rest of the vectors xi, right? And then we just say something quite crude, that all of them belong to V. Okay. So this is clearly an upper bound. Okay. And then, okay, we repeat everything here. We have P of CV. Well, these are two independent events anyway, right? So we can replace this by 2 of the x belong to V to the power, well, the number of vectors here, which is 1 minus epsilon to the n, right? And so what would we have? Will be n to the minus this plus this thing. The entropy should be in plus, right? And then you have this probability, which is, I think this even, I think it's, yeah, probably it's important to have this one here. Right. So this thing right here is n to the 1 minus epsilon d in the minus. And we have a little minus epsilon. Okay? Yes. And then time P of CV. Yeah, so sorry about that. I say that epsilon n is not in epsilon n and epsilon n minus 1 is the same. Actually, they are not. We have this, still have this one here, which is actually important because the main term here sort of cancel each other. And all we have left is the epsilon. So, right? And now we execute, we finish it the way we did before. We have to sum up over OV. Right? So here we sum up over OV as well. Again, this probability is bounded by 1. So, well, now we have this function with gamma also depend on epsilon, as we had before, something like this. Log base 2 of 16 over 15. And now you just have to optimize epsilon, and you get what I claim. And actually, after we optimize it, and actually we have a better bar than what I claim. And somebody check it and say, no, we have. I think the bar we say here is like this. But in the first version of the paper, I claim something even bigger. And then the paper was sort of accepted, and somebody said, oh no, you really have this. Things like this happen. Okay, so I think my time is sort of, so it is basically the first part of, well, I can say 15 minutes about how you begin the second part. But, I mean, you can leave right now if you want. I don't want to keep everybody too long. It's big enough suffering to sit here for 1 hour. Okay, so actually so one thing I didn't prove in the first part is why the mu helps. Right? So we claim something like this. X1 or x is in B is less than half of x. V of x 160 V, right? And so in general, I want to show that why you can expect something like this. Okay. So yeah, so not now starting the second part of the argument, and where, yeah, so where we get to 3/4. Okay, so I'm going to rewrite the whole thing as, say, the expectation, right, of the indicator event that x is in V. And now I'm going to compute everything modulo P when P is a very big prime. So P will be huge. Say, take it to be n to the n. Every kind of calculation we did here will lead to number less than this. So if you take modulo P, actually you don't lose anything. Now it is a standard things to use discrete harmonic analysis to write down as this sum, say, look at O element in ZP and E of the sum of, say, epsilon I, AI times C. Right? So A1 up to AN are the normal, well, this is a normal vector of V. Right? So x is in V if and only if the sum of AI epsilon I equal to 0, right? And well, the definition of this e to the alpha is e to the minus 2 pi I alpha, the radical the usual one you use in harmonic analysis. So you see that if this guy is 0, it will contribute 1, and if it's not 0, it will contribute 0. So that is yeah. Oh, and okay. So yeah, yeah, right. Yeah.
I alpha over p.
Yeah, of course. Yeah. Okay, what I talk about is actually the indicator event equal the other one. Now, if we take in the expectation, we take in the expectation on both sides. So the expectation here is the expectation of the product. Right? So it's the product of expectation. No, but this you can compute exactly what it is, right? It is half of cosine minus I times psi and plus half of cosine times I. Psi, so the imaginary part, of course, must disappear. So what you have is 2 pi I. Well, you know, the I is sort of bad. Let me change it to J. Oh, yes. Right. It's 2 pi of this over pi. Oh, actually, not, yeah, only of C. Okay. And now, well, we want to up about this. So it is enough. Now I can take the absolute value in the cosine. Now, if we want to do the same thing with mu, what would we have? Well, we can do the same thing up to here. Okay, and that would give you P. Now we will have mu will be 0 with this probability. Right? So we have this thing for sure. And now we'll have mu times the cosine.
One so general idea would be if you can say anything good about these AIs, we can count this efficiently. Is that what
yeah, right. Okay. Okay, yeah, so there's a small trick that actually we can get rid of the factor of 2. It is sort of an easy exercise to change that. Actually, I delete the factor of 2. Here, it's still the same. So namely, the last line equal this guy. Yeah. So it's not important of cosine of 2 things. Because it's the periodic doesn't change. Right? So now let me compare the two. Product is missing. So here I withheld the 2, right? And now, well, if I take mu to be 1/4, this guy, because of this function dominates this one. Actually, it dominates in very strong sense that every single term in the product dominates the corresponding term in the other product. Right? So at least at mu equal to 1/4, we will have something like this. Okay, that is, and that's where the method stops at 3/4, because beyond that we don't even have this. Okay, so now I'm going to do the following. I will say that for almost every V, you not only have this, you have something 100 times better. Namely, you can have this. say 1,000,000 times better for must V. And what is the reason? Well, look at one single product. I mean, the product, every term in the product is dominated by the other one. Right? And you multiply n of them together. So if the coefficient aj are sort of generous or general, then you surely should gain a factor of 1,000 by, multiply n numbers which are O less than 1 together. Right? So if you don't, and if you gain this, then you gain huge in the older estimate before. Right? You can put any constant here. So actually what we really prove is that if you look at the contribution by the middle class, they are bounded by limit of 1 to the n, thanks to this. Because here you can take any big constant you want. Even log n is good enough. Now, of course, it's not true for OV, but then we can prove the structural theorem for the rest and just simply count the number of the bad V. Right? So, and here's where the additive number theory comes about, because you see that if this doesn't hold, then one of the possibilities you can see that the aj should be in an arithmetic progression. Right? And we basically proved that. And that identify all the bad V, count the number of V, and then times the probability that all the xi should belong to V. And that kills the rest. And yeah, so yeah, most of the proof is devoted to the classification of this V. And then, okay, so I think I should stop here.
That doesn't seem to stop at mu equals a quarter. You can go beyond that, and then for some of the factors, they go the wrong way, and some of them go your way, and you have to...
Yeah, we don't... yeah, intuitively that is right, but we don't know how to do that. Yeah. Intuitively, we require something, well, we use something very strong, right? It's like L infinity norm everywhere. But yeah, what would be enough is just the L2 norm, for instance. Yes. So you just need the product to be larger, not every single term. But yeah, I don't know how to do that. Yeah. So the way we handle the bad V is that we have to look at the spectral of this function. So all the frequencies see when this thing is larger than some constant, and then show that spectral has an additive property. But the spectral set, so if I define the spectral is of C when this product, say cosine of AJC, is larger than, say, 10 to the minus 100, and this set is more or less perpendicular to the set of AJ. Right? So if I can control this, I can use inverse Fourier analysis to control AJ. But in order to control this, I need this condition pointwise. Yeah, that is the problem. Yes?
Can you explain why you chose why you just did the transfer over ZP and not the usual one over the reals? It seems like the whole thing would work.
No, because I have a Feynman theorem over ZP. I don't have a Feynman theorem over the real.
Yeah, because everything else works.
Yeah. The grounded field has no role. P we cancel at the end. Mm-hmm. In all calculation, it should cancel itself. Yeah, but the core is that at some point I have to use Feynman theorem. But yeah, I know it's very vague from here where you can see any additive structure is in a long way, even when you see the additive structure. Count this guy, which is yeah, so as the Oda said, it's really very interesting that we can control or compare these two without the pointwise domination. If you can do that, then actually you can even get to the half to the N conjecture. Because the rest of it is
So you really believe that you didn't lose in the, actually in forgetting about the cancellation? It looks like there is the first part, putting the absolute values, is a big loss. If you want to go down to 1
Yeah,
half.
yeah, we know that too, but
Actually, that seems. Okay.
I don't know anything. In all kind of proving, at least it's very hard to do anything.
Oh, I agree.
No.
I agree.